Hi and welcome to week 6 of the 8-week flavor of Introduction to Meteorology, and this video is strictly to provide a little more background on the atmospheric sounding and what goes into it and why we have them. So there's an assignment about interpreting some details from a sounding taken in Norman, Oklahoma at some date in the past. So I'm going to go through a sounding taken very recently at Shreveport, Louisiana, and there's nothing special at all about this sounding other than it's basically the same type of sounding that you're interpreting, and we'll walk through what all these crazy lines on the graphic mean. So first of all, here's the example sounding from Shreveport. Looks a little bit like the one from Norman, and this information basically comes from a weather balloon, a radiosonde is what they're called. So this is the atmospheric profile as you start at the surface and go up over, in this case, Shreveport, Louisiana. This is what the weather balloon saw on its way up in the atmosphere. This is the temperature, the moisture represented by the dew point, and the winds that were observed on the way up. So this comes from a weather balloon, and it helps describe the atmosphere over Shreveport, and in the case of your homework, the atmosphere over Norman, Oklahoma. And there's actually, we won't go into it, and there's a lot of interpretation that meteorologists do to determine whether the atmosphere is unstable enough to support big thunderstorms. A lot in winter weather situations, it's really important to know where the freezing and melting layers are as you go up, and that can determine the difference between snow and freezing rain and so forth. These are really powerful tools, and we're just scratching the surface on how to interpret the lines. We obviously won't be able to get into how to interpret the meteorology, but we will get into interpreting the data. So first things first, and I'm going to draw with my kids' Sharpies here. So you have an assignment that looks something like this. I just want to go over what each of these lines are. This is called a Skew T Log P diagram. This is the way most meteorologists look at this. Skew T means temperatures on a skewed axis, and log P means pressure is represented on a logarithmic axis. Neither one of those you really need to succeed on this assignment, but that's where the name comes from. So the first axis to look at, the first set of lines to look at, are the ones that are truly horizontal going across, and in your assignment they're basically light blue lines, and I'm going to just I'm not going to draw all over them, but I'm going to point them out on this diagram. So I've put some heavier blue marks on the very left side of those lines, and the light blue lines extend all the way across. One thing to notice is they're horizontal, and these are just pressure lines. So as you go up, the pressure associated at those lines goes down. This is simply a way of tracking how high you are in the atmosphere. Meteorologists, because of the way the math works out, often keep track of height in terms of pressure rather than feet or meters above the ground or above sea level. The point being that pressure decreases as you go up. So a meteorologist will often ask, what are the conditions at 850, meaning 850 millibars? What are the conditions at 500, meaning 500 millibars? So what these lines are on this particular sounding and on the one in your assignment are just basically knocked out at every 100 millibars, and there's several different ways to do it. And I've drawn some values on there. So as you go up, the pressure is in most places in the the pressure is near the surface about 1,000 millibars. The only exception being very high mountains, but for the purposes of this assignment, 1,000 millibars is about the ground level. And as you go up in the atmosphere, the pressure goes down. So we go from 1,000 up to 900 to 800 up to 500. So you're halfway through the mass of the atmosphere basically as you go up. And so essentially those are the lines that help you determine how high up you are in the atmosphere. So for this assignment, all it means is that's how high you are above Shreveport, and it's just a way of gauging where things are. So a meteorologist might ask the question, and I think your assignment does ask the question, what are the conditions at some level in the atmosphere? And it's just important to remember that as you read across on that blue line, you'll encounter some other lines that will describe the conditions there. So this is just a framework for what the features are. These two lines, one of them in red, and I'm going to trace over it in red here, is the temperature as you go up, and I'm kind of smoothing out some of the detail, but that's not important right now. So I've made this line bold in red. So that is the temperature of the atmosphere as you go up, and that references a slightly different set of lines. So I'm going to trace those in blue as well. And as you know, the temperature as you go up in the atmosphere tends to decrease, but not uniformly. And that's what these lines represent. So there are some blue traces that are diagonal. And you can see them here. I'll switch sides for you. So this is the 30-degree isotherm. So this is going to be tough, but at 1,000 millibars, or this bottom horizontal blue line, that red temperature trace right here is about, I don't know, 3/4 of the way between the 20 and the 30. So that would say that the temperature at 1,000 millibars is about 27.5 degrees Celsius. And then you would convert to Fahrenheit and get an answer around, I don't know, 75, 80. And that would be the temperature at 1,000 millibars. Now, if the question asks, what is the temperature at 500 millibars? So you would find the 500 millibar line, come over here and find the red trace, and you would see that based on the diagonal temperature traces, that red trace crosses the 500 millibar really close to the -10 isotherm. So the temperature at 500 millibars would be, I don't know, about -8 on this. -8 degrees Celsius. So the temperature is cooled as you've gone up in the atmosphere. And you basically use these diagonal lines to determine the temperature at any given point up along the way. It's a Skew T diagram, meaning that the temperature is on a, how do I do this? On a skewed axis. All right, so the other line is green, and that represents the moisture content through the dew point temperature. Uses the exact same slanted temperature lines, but the green is the dew point temperature. So here we are on this graphic. You can see while the temperature goes up relatively uniform, or not uniformly, but fairly smoothly on the way up, the dew point has a lot of noise in it, and that's kind of typical. So areas where the dew point gets way over here into some really cold temperatures, that's -20 and 30, that's very dry. The basic thing to remember is the dew point temperature and the temperature itself reference these skewed lines. You find the temperature by interpreting between the skewed lines. So you find the pressure level that you're interested in, let's say 500. The temperature was something like -8, we decided, where that red line crosses the 500 millibar height. It's most of the way between 0 and -10. I'm going to say it's about -8. The dew point temperature is on this next diagonal line. So the dew point temperature at that point would be about -20. And that's how you do it. The last thing on here are the winds. Here's a representative wind at the 500 millibar level. It's plotted on the right side. So if you take 500 millibars and you go all the way to the right, you'll see that the wind is depicted as out of the west-southwest at 30 knots or 30 miles an hour. And so the winds, as you go up, generally get stronger and they generally get more westerly. So if the question asks you what are the winds like at a certain level, again, first thing you do is you find the level you're asking about. In this case it was 500. You stay on that 500 millibar line until you come over here and find the winds, and that's where the winds are going to be. Again, all of this and then all of this stuff up here is just Hocus Pocus photograph stuff that is meant to frighten and confuse all of us. That's actually the severe weather folks really like that as well. So again, there are actually other lines running around on there. They're not important for this class. The main thing is to know that the pressure levels get lower as you go up, and they're depicted as horizontal lines. And so when the question asks what is some condition like at say 800 millibars, you go up and you find that 800 millibar line, and then you find where the temperature and then the dew point cross that line. And then you can have the winds at that line as well. And the temperature and dew point will be plotted against those skewed axes. So it takes a little bit to get used to, but it is ultimately, it's actually a really powerful tool. It's kind of a genius design. All of those other kind of curved lines on there fit kind of magically, and you can do some really important measures of instability, a lot of thermodynamics type stuff, how much energy is locked up in the atmosphere that could be released by thunderstorms and all of that. So while it is a little non-intuitive in the way that you look at it when you first approach it, it's actually quite powerful. So this is just an exercise in getting used to the fact that, first of all, there's a weather balloon taking values as you go up in the atmosphere and reporting that. And we have that available for, I don't know, 50, 60, 70 sites across the United States. They take them twice per day. And that actually is important information. And that weather data as you go up in the atmosphere is organized by pressure level. I know I've beaten that to death, but that's why we have 1,000, 900, 800, 700, 600 as you go up millibars instead of so many thousand feet. We organize our data and our thinking in meteorology by the pressure level as you go up. That is all for this assignment. I hope you have a great week, and thanks for your patience in me stammering through this video. Thank you for your service, especially those of you who are still actively serving. All right, bye-bye.